So, probability. Before going to discuss about the probability, first of all we need to know some basic concepts related to probability. Then only you can understand what is actual probability, what is its applications. So first, before going to discuss probability, first we need to know what is a random experiment. A random experiment. So random experiment means it is an experiment. We know we did so many experiments. So in experiment, actually after completion of experiment we are going to get result. But here in this experiment, this is a type of experiment in which outcomes of the experiment are known, but outcome of a particular trial is not known. What I am saying? Well, before conducting the experiment, we know what are the outcomes we are going to get. But what is the exact outcome we are going to get for a particular trial is not known. That type of experiment is called random experiment. So here, this experiment can be done n number of times. An experiment which can be done any number of times. Which can be done any number of times or n number of times, in which outcomes of experiment are known. Outcomes of experiment are known. Outcomes of the experiment are known well before conducting, but outcome of a particular trial is not known. Outcome of a particular trial is not known. That type of experiment is called random experiment. Here you may have one doubt, what is trial? So trial means nothing. Trial is any performance of the experiment. What it means? Any performance of the experiment is trial. If you conduct an experiment 10 times, it may contain 10 trials. If you conduct an experiment 5 times, it contains 5 trials. If I am doing experiment first time, that is called first trial. If I am doing an experiment second time, that is called second trial. If I am doing an experiment fifth time, that is called fifth trial. That is trial. So here you can understand very clearly, a random experiment is an experiment which can be done any number of times, your wish, but in which these two conditions are mandatory. Outcomes are known well before conducting the experiment, but outcome of a particular trial, when you are doing that experiment, you cannot guess what is the exact outcome you are going to get. That type of experiment is called random experiment, which is foundation for probability. So here, an experiment which can be done like this, that is called random. Can we guess what are the type of experiments we are seeing in our day-to-day life? Examples, the best examples for this is tossing a coin and throwing a die like this. Like this, so many experiments we can discuss. We can give examples for random experiment. If you take the first example, tossing a coin. If you toss a coin, well before tossing a coin, you know what are the outcomes you are going to get, tail or head. But can you guess what is the exact outcome you are going to get for a particular trial? No, we cannot guess. That type of experiment. And if you throw a die, you know what are the outcomes you are going to get, 1, 2, 3, 4, 5, 6. But can you guess what is the exact number you are going to get for a particular throw? No. Not only these type of examples, if you take 10 sheets, 10 small sheets, numbered from 1 to 10, give numbers 1, 2, 3, 4, 5, 6 like that. Shuffle that 10 sheets, simple sheets. Take one sheet randomly. Can you guess what is the exact number you are going to get? No. But you know what are the outcomes you are going to get? 1 to 10 numbers. That type of experiment we can call it as random experiment. You know one spinning wheel which numbered from 1 to 12 like that, there is an indicator. If you rotate that wheel, after some time it will stop at one number. That indicator shows one number. Can you guess what is the exact number it is going to show after some time? No. But you know what are the numbers you are having there. From that numbers only you are going to get one number. These are all some examples for random experiment. Are you clear? What I am saying, in random experiment, we are going to know all the outcomes well before conducting the experiment. If you can write that all the outcomes in a set, that is called sample space. This is universe for random experiment. We represent this one with a letter S, sample space, which is universe for random experiment. What is a sample space? Sample space is nothing. It is set of all possible outcomes. Set of all possible outcomes of a random experiment. Random experiment is called sample space. Set of all possible outcomes. As many you will get, that all you need to write in a set. Example for tossing a coin, tossing a single coin, S is 2 elements. For throwing a die, S is 1 to 6 numbers. 1, 2, 3, 4, 5, 6. So for one coin you will get like this. For one die you will get like this. Now you can understand, before tossing coin you know what are the outcomes you are going to get, these two. That too, if you write in a set, that is called sample space. Before throwing a die you know what are the numbers you are going to get. The total numbers if you write in a set, that set is called sample space. These are the elements in S. For one die you will find 2 elements. For one die you will find 6 elements. For one coin you will find 2 elements. But if you have n coins are tossed, if n coins are tossed, then n of s will be 2 power n. If you toss one coin, you will have 2 outcomes, 2 possibilities. Total outcomes 2. But if you toss 2 coins simultaneously, what happens? You may get tail, tail, head, head, tail, head, head, like 4. So if you write in the place of n2, you will get 4. Similarly, for one die you will have 6 outcomes. For example, n dice if you use, then in n of s you will find 6 power n elements. For one die 6 power 1, for 2 dice 6 power 2, 3 6 cube, like that. So this is sample space, which is universe for random experiment. The random experiment contains some outcomes, all outcomes. If you write in S, that is called sample space. For example, set of all possible outcomes is random experiment. If you write some outcomes in separate set, what we can call it? We will call it that one as event. Event. Event means nothing. Subset of sample space, or simply we can say set of outcomes. Set of outcomes of a random experiment. Set of outcomes of a random experiment is event, or simply what we can say, subset of sample space. Yes, subset of sample space. That means, for example, if I write, for throwing a die, A be the event of getting these numbers. For throwing a die. See here, the elements which you have in A, all the elements do you have in S for throwing a die? 2, 3, 4 you are having here. Do you have 2, 3, 4 here? Yes. If all the elements, whatever you are having in A, if you have in S, that is called subset. The elements which you have in one set, if you have all the elements in S, then we call this set is subset to S. Now A is subset. Now we can call A as event. So event means nothing, subset of a sample space. Or if you write few outcomes of a sample space separately in a bracket, in a set, that we can call it as sample space. Like that, you can write B is a set event which has tile. This is an event of getting tile when a coin is tossed. If you see, this tile is here, then this B set is subset to S for tossing a coin. Again B becomes event. Like this, in an event, if you find only one element, one outcome, we can call this one as simple event or elementary event. Simple event or elementary event. That means nothing. In an event, if you find only one outcome. The outcome of an experiment individually we can call it as elementary event or simple event. Are you clear what is event, what is sample space, what is random experiment? An experiment which can be done any number of times, in which outcomes of the experiment are known well before conducting, but outcome of a particular trial is not known. That type of experiment is called random experiment. If you write set of all possible outcomes of a random experiment in like this, then that is called sample space. Set of all possible outcomes, if you can write in a set. Subset of any sample space, we can call it as event. Or set of few outcomes of a random experiment, we can call it as event. In an event, if you find only one outcome, one element like this, we call that one as simple element, simple event or elementary event. Any doubts you may express. Mutually exclusive events. You can say two events are mutually exclusive based on set theory. If A comma B are any two events, if A intersection B equal to 5, then A comma B are called mutually exclusive events. Mutually exclusive events. So two events are said to be mutually exclusive if A intersection B equal to 5. That means A and B should not have common elements. Here I said, what is event? Event is set of outcomes. If A is some set of outcomes, B is some other set of outcomes. If you won't find any common outcomes for A comma B, then we say A, B are mutually exclusive events. Happening of one event does not prevent the happening of another. That type of events. Simply we can say like this. Example, for throwing a die, if you take, for throwing a dice, A be the event of getting like this 2, 3 numbers. B is another event of getting 4, 5. Now if you find A intersection B, you will get an empty set. So you cannot find common elements in both the sets. The elements which belongs to A and B are called A intersection B elements. Can you find that type of elements in these two events? No. That type of events we can call it as mutually exclusive events. Similarly, we have another type of event, exhaustive event. Exhaustive event. Two events are said to be exhaustive events, like A comma B. A comma B are any two events. Any two events. If A union B equal to S. If A union B equal to S, then AB are called exhaustive events. Union means you can combine all the elements in A and B. All the outcomes which you have in A and B, if you write in one set, then we call that one as union. If you take the union of two events, if you get a sample space, then we call A comma B are exhaustive events. What I am saying, for example, if you take two events, if they contains all possible outcomes of a random experiment, then AB are called exhaustive events. Set of all possible events for a random experiment, if you get in two events, the two events we can call them as exhaustive. For example, the same example I am taking for throwing a die. For throwing a die, if you have like this, A is one set which contains 2, 3, 4, 5. B is another set which contains 1, 2, 6. If you observe these two events, A is an event, B is another event. If you observe these two events, you are having set of all possible outcomes of a random experiment throwing a die. So when you throw a dice, you will have 1, 2, 3, 4, 5, 6 outcomes. The total 6 outcomes, if you can find in AB, we call them as exhaustive events. If you want, you can check this one, A union B. A union B means combine these two sets. If any element is repeated, you can write one time. 1, here 2 is repeated, write one time. 3, 4, 5, 6. Which is sample space for a random experiment of throwing a die. So here AB are exhaustive events. Exhaustive events means if two events contains all possible outcomes. For example, complementary events. If two events satisfies both the conditions, what I written there, A intersection B phi, A union BS. If A comma B are two events and if A intersection B is phi and A union B equal to S, A intersection B phi, A union B S, then A comma B are called complementary events. Both the condition it should satisfy. Then we call them as complementary events. So, for tossing a coin, if you take one best example, A is only one outcome getting tail, B is another outcome getting head. Then what happens? A is an event of getting tail when a coin is tossed. B is an event of getting head when a coin is tossed. See here, what is A union B? A union B will get TH. What is A intersection B? Intersection means you need to write the elements which belongs to both A and B. Can you find that type of elements which belongs to both sets? No, we cannot find. So this is an empty set. So which satisfies both the conditions. In the case of probability concepts, if A is an event, its complement is written like this. Its complementary events is represented like A complement, A power C. Probability of A plus probability of A complement equal to 1. So here also the elements which belongs to A, they won't belongs to A complement. The elements which is in A complement you cannot find in A. But if you combine A and A complement, you will get complete set like S. So that type of events we call them as complementary events. Any doubts anywhere you may express? Any type of event? So what is actual probability? Probability definition, classical definition we are going to discuss. How to calculate probability of an event. In a random experiment, if you have n events, small n elementary events, in that for a particular event for which we need to find probability, small m events are favorable, then probability of that event is m by n. So what we can understand? Probability is a ratio between favorable events to total number of outcomes. Favorable events to total number of outcomes. We can call that one as probability. So what I am saying, if a random experiment contains n elementary events in which m are favorable to a particular event for which we need to find probability, then probability is ratio between favorable events to total number of outcomes. In that random experiment. So what I mean to say is, probability is nothing. Probability equal to favorable events by total number of outcomes. This I written here, if an event contains total n elementary outcomes. That means total is n, in which m are favorable. So m by n we can write. Out of n elementary events, m are favorable. So we have probability value is ratio between m and n. Simply what we can write, probability of any event A can be written like this. Number of elements in event A by number of elements in S. A be any event in S in the random experiment. Like this also we can find probability of A. N of A means number of elements in A event. N of S means number of elements in S. S means sample space. set of all possible outcomes. Total number of outcomes you will get in S. Okay, what I am saying, if you want to calculate probability of getting head when a coin is tossed. When a coin is tossed, what is the probability of getting head? If you toss a coin, you will have two possibilities, T heads. So total number of possibilities you are having is 2. How many heads you will have? Only one head. So favorable is 1. 1 by 2 will be the probability of getting head when a coin is tossed. Like that, one can easily find out if he can evaluate favorable and total number. So like this we can evaluate probability. So with the probability definition, one can easily understand some other types of events like sure event. Sure event, or we can call this one as certain event. Sure or certain. What is a sure event? Name itself says meaning. An event which always happens in the random experiment is called sure or certain event. An event always happens. For example, an event of getting a tail and head, a tail or head when a coin is tossed, that is sure event. I am tossing one coin, I am asking to get tail or head, definitely will get tail or head. They have 100% chance. That type of events are called sure or certain event. The probability of sure event is 1. The probability of sure event 1. That means it 100% chance it has. If you multiply with 100, you will have 100%. Here also, I calculated probability of getting when a coin is getting head when a coin is tossed. 1 by 2 means we know 0.5. If you multiply with 100, you will get how much chance, percentage of chance you are having of getting head when a coin is tossed. That is 50%. So here 100%. Just now I said one example for sure event. If you want, you can calculate probability for that event, you will get 1. What is that example I said? When a coin is tossed, getting tail or head. For this probability, favorable events both tail or head are favorable. So favorable are 2 by total you are having 2. 2 by 2, 1. Like that one can easily calculate the probability of sure event like 1. So another event we are having impossible event. Impossible event. That name itself indicates what is the exact definition of this impossible event. An event which never happens. An event which never happens in the random experiment. An event which never happens in the random experiment is called impossible event. For example, the same experiment which I had taken for sure event, if you take like this, that becomes impossible like this. A coin is tossed. Here the event of getting tail and head, is it possible? I am tossing one coin, I am asking for both tail and head. Can you get tail and head on one coin at a time? No. That type of events are called impossible events. A die is thrown, I am asking to get what is the probability of getting 7. There is no case of getting 7 in when a die is thrown. That is impossible event. For the impossible event, probability of impossible event is 0. So So from this one can easily understand an event which always happens in the random experiment has a probability 1. An event which never happens in the random experiment has probability 0. So from this, what you can understand, probability always lies between 0 and 1. It should not cross 1, it should not less than 0. So axioms of probability, we can call this one as the probability in axiomatic way. So here, axiom means a trivial statement which do not require proof. Theorem, you know, theorem is a statement which may be true or false, but you have to prove that is true. Proof is required. The axioms are trivial statement, true statement which everyone can accept without proof. Like sun rises in the east, there is no need of proof. That type of statements in probability also we can find. There are 3 axioms of probability. Axiom 1. Probability always lies between 0 and 1. Or probability of any event always greater than or equal to 0. Where A be any event in S. Any event in S. What it means? Probability always positive. This is called non-negativity axiom. Probability never be negative. One is saying that one. This one saying probability value always lies between 0 and 1. It may be least case 0. The maximum value are having 1. It should not cross 1. That is the basic principle which do not require any proof. Generally, we say one event is happened or not using percentages up to 100%. There is 50% chance, there is 70% chance, there is 100% chance like that. We may say 200, 150%, but there are no 200%, 150%. The probability of happening one event maximum is 100% chance only. 100% means sure event. Okay, now coming to second one. Probability of sample space is 1. What it means? The totality it represents. Probability of sample space. Sample space means we all know that is the universe for random experiment. Whenever if you calculate probability of the total possible outcomes, the favorable will be the same number, total number will be same number. Same number by same number, what you will get? 1. Or I said one simple formula for finding probability of A. You know that n of A by n of S. Using this formula, if you can calculate probability of S, what happens? In the place of A, you need to write yes. If you write in the place of A, yes, what you will get? N of S by S. N of S. N of S, N of S get cancelled. 1. So, which is very most important axiom in every axiom is important. This one we use repeatedly. Whenever if you want to take total probability value, there you need to take 1. That is totality of probability. Coming to third one, last one. If A comma B are mutually exclusive events, A comma B are mutually exclusive events, then P of A union B equal to P of A plus P of B. Whenever A, B are mutually exclusive events, you know, when we can say two events are mutually exclusive, two events are said to be mutually exclusive, if A intersection B equal to 5. If A intersection B equal to 5, then we say they are mutually exclusive. When A intersection B equal to 5, then probability of A union B is sum of individual probabilities P of A plus P of B. We use this one whenever A, B are mutually exclusive. So these three are axioms of probability. Very most important. Are you clear what is axiom? A statement which won't require any proof. A true statement. So like this, these three you need to keep in our mind while doing any problem in probability. Keep this point. The answer should be lies between 0 and 1. And the total value should not cross 1. And whenever A, B are mutually exclusive probability, you need to find like that. But whenever A, B are mutually exclusive, probability of A union B is probability of A plus probability of B. But what is actual probability of A union B whenever A, B are not mutually exclusive? We will discuss in addition theorem on probability. Addition theorem on probability describes about what is actual P of A union B. A comma B are any two events in S, then P of A union B equal to P of A plus P of B. That means P means probability of A plus probability of B minus probability of A intersection B. This is actual probability of A union B. This is called addition theorem on probability. So in this, we won't get probability of A intersection B value when A, B are mutually exclusive. Just now I said, when A, B are mutually exclusive, probability of A intersection B becomes 0. Because A intersection B 5 means the number of elements in A intersection B are 0. 0 by anything, 0. So probability of A intersection B becomes 0. That's why probability of A union B will be probability of A plus probability of B. Whenever A comma B are not mutually exclusive, that means simple. We will prove this one with two steps. When A intersection B is not equal to 5. Because if A intersection B equal to 5, that is trivial. Probability of A union B will be probability of A plus probability of B. That one is trivial. When A intersection B equal to not equal to 5 means, if you observe in Venn diagram, you can understand how A B will be. So here the universe is yes. Let A be the event and B is another event. Because A intersection B not equal to 5, you will have A B like this. This is called A intersection B part. So this is called only B part. This part we can call it as, this is total B. In total B except A intersection B remaining thing. What I am saying, B minus A intersection B, we can call it as this part, red line part. Now I am writing A union B like this. A union B will be A union this part. This is A plus this one. B minus A intersection B. So we all know that here very clear. A comma B minus A intersection B are mutually exclusive. Mutually exclusive means they are disjoint, they are not joining. from axiom 3, what you can write, if A, B are mutually exclusive, we can write in the place of union plus. The probability of A union B will be probability of A plus probability of B. Like that, we can use that one here. Probability of A plus probability of B minus A intersection B, because these two are mutually exclusive from axiom 3. Now, this can be written like this using one fundamental set theory principle. If A subset B, then probability of B minus A can be written as probability of B minus probability of A. If A subset B, like that, here A intersection B is one subset in B, right? One small part in B. So when A intersection B is subset of B, this can be written using this. You can write probability individually. Then what happens? Probability of A plus, probability of B minus, probability of A intersection B. So this will be the proof which we need to prove. Addition theorem on probability. When A intersection B is not equal to 5. When A intersection B equal to 5, that is trivial. If you want, you can add that one as case 1 in addition theorem proof. Case 1, when A intersection B equal to 5, this statement you can write. Case 2, when A intersection B not equal to 5, you can prove like this very easily. Any doubts you may express in addition theorem on probability. Addition theorem on probability. So, axioms we will discuss, probability axioms, 3 axioms. Third axiom says that if A comma B are mutually exclusive events, then P of A union B equal to P of A plus P of B. Whenever A, B are mutually exclusive events, then P of A union B. But what actually P of A union B we are having, that we will discuss in addition theorem on probability. If A comma B are any two events in sample spaces, B are any two events in S, then P of A union B equal to probability of A plus probability of B minus probability of A intersection B. So this is the statement of addition theorem on probability. Addition theorem on probability. So this is actual statement. This we are going to prove now by taking two cases. One case, if A intersection B equal to 5. Another case, if A intersection B not equal to 5. So we will prove this by taking two different cases. Case 1, if A intersection B equal to 5. If A intersection B equal to 5, then A comma B are called mutually exclusive events. When A intersection B 5, then A comma B are mutually exclusive events. When A comma B are mutually exclusive, using axiom 3. Axiom 3. Axiom means a true statement which do not require any proof. When A intersection B equal to 5, the axiom 3 says that probability of A union B, probability of A union B is probability of A plus probability of B. So from axiom 3 of probability. Third axiom. So when A intersection B equal to 5, probability of A union not required any proof, there is a trivial statement, that is nothing to prove. Probability of A union B becomes probability of A plus probability of B. This case we can easily observe in Venn diagram when sample space is universe for random experiment. A is one set, B is another set, both are disjoint sets. Disjoint sets, they are not joined. So in section B, you cannot find any common part. So this is the case where we proved probability of A and B is probability of A plus probability of B. Coming to case 2, when A intersection B not equal to 5. When A intersection B not equal to 5 means there is some intersection part for both A and B, like this. AB has some common intersecting point. So here you can observe this part is A intersection B. This part you won't find there. This is A set, B set. That part is, we call that one as A intersection B part. So coming to this part, this vertical line part, what we can say? This vertical line part we can name it as B minus A intersection B. Here this one completely B. In B, if you subtract this A intersection B part, you will get A minus this part. B minus A intersection B. So, except A intersection B part in B, we named it as B minus A intersection B. Now, how we can write from Venn diagram, how we can write A union B? So A union B is A, this total part, union this vertical lines part, which is named as B minus A intersection B. So A union B is union of A and B minus A intersection B. Here one thing clear, from that Venn diagram one can easily understand, again A and B are again A, B minus A intersection B are two mutually exclusive events. Mutually exclusive events. When A comma B are mutually exclusive events, from axiom 3 of probability, what we can say? Probability of A union B is probability of A plus probability of B. Like that, probability of A union B minus A intersection B will be probability of A plus probability of B minus A intersection B, because A and B minus A intersection B are mutually exclusive events. So, from axiom 3, what we can say about probability of A union B? Probability of A union B minus A intersection B, like this we can write fast. This can be written using axiom 3, probability of A plus probability of B minus A intersection B. Using axiom 3 of probability, we can write this one as sum of individual probabilities. Now, from set theory, we all know that if A is subset of B, then probability of B minus A can be written as probability of B minus probability of A, when A is subset of B. So the same case we are having here also. A intersection B is subset of B. If you observe this Venn diagram, this is A intersection B part, this complete one is B. In B, A intersection B is small part and A intersection B subset to B. When A intersection B is subset to B using this one, what we can write? Probability of B minus A intersection B. Probability of B minus A intersection B can be written as probability of B minus probability of A intersection B. Using this axiom, what we can say here? Here, A intersection B is subset of B. That's why we can write probability of A union B like this. So finally, the statement is probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. This is called addition theorem on probability. Any doubts you may express? Conditional event. So name itself says, meaning this is one type of event which has a particular condition. Conditional event means that is an event of happening one, an event of happening one after happening another, after happening another, an event of happening one after happening another. That is called conditional event. Happening one event after happening another event. These type of situations we see in so many problems. For example, a box contains two different colors of box. Randomly we are picking up one ball. There is a question like this: what is the probability of getting one color ball after getting another color? For example, black and red. What is the probability of getting black ball after getting red ball? So these type of situations we use the conditional event concept. Happening of one after happening another. For example, if A comma B are any two events in S, then conditional event of A comma B is denoted as like this: A given B. We read this one as A given B. A given B. A given B. So this is conditional event of A B. What is A given B? A given B means happening of A, happening of an event A after happening B. Happening of an event A after happening B. If you write like this, A given B, it means happening an event A after happening B. That means the first event is B, second event is A. Here, first event is B, second event is A. A given B means happening of an event A after happening an event B. Similarly, the B given A is represented like this: happening of B after happening A, after happening A. So here also you can easily identify the first one and second one. The first one is A event, second one is B. So these are the notations to represent a conditional event. Conditional event means nothing, happening of one event after happening another, occurring one after occurring another. From this we can easily define what is conditional probability. Conditional probability. So conditional probability means nothing. Very simply, in one word, what we can say, conditional probability means probability of conditional event. Finding probability for these type of events, we named it as conditional probability. Conditional probability means probability of happening one after happening another, after happening another, we can say conditional probability. So simply what we can say, the probability of conditional event. Already I said how to represent a conditional event. Like this we can represent A given B. Probability of A given B. Probability of A given B we are discussing now. The probability of A given B is probability of A intersection B by probability of B. Similarly, probability of B given A is probability of B intersection A by probability of A. Okay. These can be written in different way when A comma B are independent events. When A comma B are independent events, then what happens? Probability of A intersection B can be written as probability of A into probability of B. Then what about probability of A given B? Probability of A given B, in numerator, probability of A intersection B becomes probability of A into probability of B. If you write here probability of A into probability of B get cancelled, you will have only probability of A. Similarly, when A comma B are independent events, probability of B given A is, here you will get probability of B into probability of A. Probability of A get cancelled, you will have probability of A. So this is one important application in conditional probability. Whenever A comma B are independent events, what is probability of A given B? What is probability of B given A? So from this, one can easily define what is the multiplication theorem on probability. So multiplication theorem you can easily understand from conditional probability. The multiplication theorem on probability says, multiplication theorem on probability says, if A comma B are any two events, if A comma B are any two events in S, any two events in S, then probability of A intersection B can be written as probability of B into probability of A given B, that equal to probability of A into probability of B given A. So this is actual statement of multiplication theorem that we can easily understand from conditional probability. From conditional probability one can easily understand the statement what I written clearly. From conditional probability we all know that probability of A given B is probability of A intersection B by probability of B. From this we can easily derive what is probability of A intersection B. So probability of A intersection B can be written as probability of B into probability of A given B. Similarly, if you take this case, probability of B given A, probability of B given A is probability of B intersection A by probability of A. From this, what is probability of B intersection A? Probability of B intersection A is probability of A into probability of B given A. So if you observe these two, if you assume this one as 1 and 2, from 1 and 2 what we can observe? We all know that A intersection B equal to B intersection A in set theory. So A intersection B means the elements which are common to AB, the same elements you will get in B intersection A also. That means probability of A intersection B, probability of B intersection A also equal. So from 1 and 2 what we can say very easily, probability of A intersection B can be written as probability of B into probability of A given B, that equal to probability of A into probability of B given A. So this is, we can treat it as a proof of the multiplication theorem. Very simple way we can prove. Okay, so are you clear what is conditional event and conditional probability multiplication theorem on probability? Any doubts you may express?